Hello everyone, Assalamualaikum and good day. So now let's proceed with the next subchapter, which is limits involving trigonometry. So basically we have actually gone through on how to solve limits involving trigonometry in previous lectures, and now we're going to look into let me delete this one if I can. Yep. Okay, now we can just skim through another example. Okay, this is just a straightforward example 1.12. Okay, before that, if you refer to this table 1.5, this just show the limit properties for the basic trigonometry functions. And like I said just now, we have learned about squeeze theorem. Okay, these two functions, limit functions, you need to remember. And so now we go into example 1.12. So to answer the first question here, first Roman here, which is limit as x approach to pi over 3 for sine x plus cos x. So this is kind of a straightforward question. You can just straight away plug in the value of x equals to pi over 3 into the limit function, and if you try to solve it, you may get this as your final solution. Okay, now we go to the second question, 2 Roman. We have here limit x approach to -1. Okay, for the function 2 power of x pi over 2. So in this question as well, we just need to straight away plug in the x equals to -1. Okay, so if you if I can write it down here, so you know that sine 2 power of -1 times pi over 2, so you may get sine, okay, this is 1/2. Okay, 2 power of -1 is 1/2 times pi over 2, and then you may get sine pi over 4. So sine pi over 4, if you straight away use your calculator, you may get 0.707. Okay, or it's similar to square root 2/2. Now next question, you may need to use, okay, the third Roman here. So if I can write down the question for you here, so that I don't need to scroll up and scroll down. Okay, x approach to 1 cos x squared minus 1 over x squared minus 1. Okay, now you can use squeeze theorem to solve this question. Yeah, as you can see, it's a combination of use substitution and squeeze theorem. Okay, now we pick u equals to x squared minus 1. This is going to be our use substitution, and then we were going to apply the squeeze theorem limit. Okay, before that you need to define the limit approach. Okay, since we already changed the x into u, so we define here, this is the original one as x approach to 1, so we already changed it into x squared minus 1. So x squared minus 1 is also approaching to 0. Okay, why? Because you know x approaching 1, so as x squared minus 1, we also will get 0. Okay, this is I don't want to make you confused about this. So x approach to 1. Okay, now we have x squared minus 1 is approaching is approaching what value, right? So you just substitute this value into here. So if you substitute, you will get 1 squared minus 1. So your answer will get 0 actually. So that is why x squared minus 1 approaching to 0, so does the u will approach to 0. Okay, so this is how we define the limit, the u limit, and then we can rewrite again using the latest substitution here. So limit u approach to 0. Okay, and then we have here cos u minus 1 over, so x squared minus 1 is also u. Okay, we just plug in u over here, and since we want to apply squeeze theorem, so squeeze theorem is limit x approach to 0. Okay, 1 minus cos x over x. Now we have cos u minus 1, so we need to rearrange it so that it will become the same by putting negative in front here. So minus, okay, 1 minus cos u divided by u. So since this squeeze theorem is equals to 0, so basically we will obtain our final answer as 0. Okay, now we go to the fourth Roman. So let me write down the question for you. Limit x approach to minus 3 over 2 sine 2x plus 3 over 2x squared plus x minus 3. So in this question, the first thing first that you need to do is that you need to factorize the denominator, okay, before you can apply the squeeze theorem. So you factorize it first, and then we apply the u substitution. Only then we can apply the squeeze theorem. So again, when you apply u substitution, you need to redefine the x approach here to become u approach. Okay, u approaching to what? So you just simply straight away I'm plugging in the factorization here, okay, for the denominator part. Now as for the u substitution, if you notice that the denominator, okay, if I can write down here, limit x approach to minus 3 over 2, we have sine 2x plus 3, and the denominator also got the same 2x plus 3 times x minus 1. Just a little reminder, you cannot straight away cancel 2x plus 3 at numerator with denominator over here. You cannot do that, it's wrong, because here 2x plus 3 at numerator is actually the variable of the sign, okay. So you cannot simply cancel like that, okay. Now, okay, so we continue with this part. Okay, so we know that we want to substitute u equals to 2x plus 3, am I right? Again, you need to define the u here. So we are no longer using x, okay. So u here you need to define as this one. This is crucial step. So as x equals to minus 3 over 2, so we have 2x plus 3, okay. It's similar like we did here. So x, if you put x equals to negative 3 over 2, so since x is approaching negative 3 over 2, so we equal the value here, and then we plug in the u substitution, okay, approaching to what? So we just plug in it over here. What you will get is minus 3 plus 3, so it becomes to 0. Therefore 2x plus 3 is approaching 0, and so does the u approaching 0, because u is equals to 2x plus 3, right? So here u approaching 0, and this will become sine u, okay, over u. Okay, and then we still got another variable x here. Okay, since x is no longer exist because we already changed to u, so we need to rearrange the x here to become u. So in order to do that, okay, you need to make a little modification. Okay, we already pick u equals to 2x plus 3. Okay, u to x plus 3. We interested to get x, so basically u minus 3 equals to 2x. Therefore x is equals to u minus 3 over 2. So here x here is u minus 3 over 2 minus 1. Okay, and from here what you can do is that, okay, you can split them up, okay, using the limit properties, limit product properties. So limit not x, should be u. Okay, so limit u approach to 0 for sine u over u times limit u approach to 0 for 1 over u minus 3 over 2 minus 1. So this one, you know, this is Squeeze theorem, it is equal to 1. So 1 times, so this is basically you can just plug in 0 here, and what's left is that you will get 1 over minus 2 over, sorry, minus 3 over 2 minus 1. So if you carefully solve this, you will get, okay, minus 1 over, okay, 5 over 2. So in other words, your final answer is minus 2 over 5. Okay, it's quite a bit long for this part, but eventually if you study again this example, you will get what I mean. You need to redo it again, redo the question. Okay, now we may proceed to, so for this exercise you may need to do it by yourself, exercise 1.11. okay, now we go for limits involving infinity. Okay, or before that, let me write down the answer for this question so that you can double check your answer. Let me check first. Okay, so this is 0, this will be 5 over 3, and this will be 1. Okay, what happened to my 1? Okay, this should be 1. Okay, is that clear? So try to do this one at home. Now we go to limits involving infinity. So okay, as for the limits involving infinity, okay, we have like two definition actually. It's either limit at infinity or infinity limit. So basically limit at infinity is when x approaching plus minus infinity, whereas infinity limit is when x approach to any number and the final answer will be infinity, plus minus infinity. So that's the difference. One is when the involving the x approaching infinity. The other one is when the answer for that limit function is equals to plus minus infinity. Now we start with limit at infinity first. So you know that infinity is not represented by a real number, and the symbol here, the infinity symbol, is used to describe the behavior of a function when the values in its domain outgrow all finite bounds. Okay, so it's either if when x okay, if I can draw the okay, let me change the color first. if I can draw the number line here. Okay, so this is x, this is fx or y. So it can be when x approaching infinity. Okay, it's something like this one, x approaching infinity, what happened? Okay, if x approaching infinity, what happened? Okay, so this is when x approaching positive infinity, and this is when x approaching negative infinity. Okay, from the this is from towards the negative infinity, this is towards the positive infinity. Okay, so we can look into example figure 1.7, which illustrate the graph for fx equals to 1 over x. So basically fx equals to 1 over x is something like this, actually similar to the one that I draw here. Okay, but never mind, just draw it down here. Okay, so this is actually 1 over x. Okay, 1 over x. This is for fx equals to 1 over x. This is our fx, this is our x. Okay, so as x approaching infinity, so if you look closely, this one okay, approaching infinity, positive infinity, it is actually will go towards 0. Okay, approaching 0. So that is why if we can write down over here, limit x approach to infinity for 1 over x is equals to 0, and when the x approaching negative infinity, okay, the outcome will also becomes 0. Okay, so this is for this wait, yeah, I'm not sure what happened. Let me cut that one. Okay, this is when approaching, wait, yeah, I don't want to done. This is what happened. Okay, let me check what happened to my no, I don't want this one. Let me delete it. Yeah, sorry. So this is basically sorry for the glitch. So this is for this graph. Okay, this is referring to this graph. Yeah, okay, and then the line y equals to 0. Okay, so y equals to 0 is over here. This part, if I can highlight it, yeah, is known as the horizontal asymptote. So this is horizontal asymptote of the 1 over x graph. Okay, so by definition, the line y equals to b can be any number, is a horizontal asymptote for the graph function if either limit x approach to infinity equals to b, or from the x approaching negative infinity is also equals to b. So this is basically referring to this graph that we discussed just now. Okay, and yeah, this is the graph, okay, that I redrawn just now. And now there is a special case when the limits, okay, involving infinity, it deals with the quotient function or fraction function. So fraction or quotient, it means that fx over gx as x approach to infinity. So there is one special step that you need to do, which is, okay, in this example, if you have fx over gx, so fx is the numerator and gx is denominator. What you need to do is that, okay, you need to you need to divide the numerator and denominator by the highest power of x in the denominator. Okay, okay, that's the first step, divide by the highest power. And then when we want to evaluate the expression, when we insert the limit value, we are going to use the infinity properties as stated in table 1.6. So what is infinity properties? So this is the infinity properties. Any number, a is any number, divide by plus minus infinity. For example, 2 divide by minus infinity, or 2 divide by infinity, your answer will be 0. And 2 can not only 2, it can be 100, it can be 1, it can be -1, any number. Okay, now okay, if infinity divide by a, and a, okay, a is either positive greater than 0 or negative less than 0, it depends. So your answer will be, if the a is positive, you will get infinity, and if infinity divide by negative a, your answer will be negative infinity. Okay, this is for this example of 2 and 3 property infinity limits. And then if infinity times a, you will get positive infinity if a is greater than 0, and if a is less than 0, okay, so your outcome will be negative infinity. And then if infinity plus minus any number, your answer should be infinity. Okay, and then if negative infinity plus minus any number, your answer will be negative infinity. So this one, for the operation plus minus, it much dependent, your final answer it much dependent on the positive or negative sign of the infinity. And finally, if any number divided by 0 or 0 over 0, it is undefined. Okay, alright, so this is infinity properties. So if we look into example 1.13, find limit for 5x over sine x, 5x plus sine x over x as x approaching infinity. So if you can write it down, your answer like this: x approach infinity for 5x plus sine x over x. So here, what you need to do, no need to straight away apply in the infinity value. You might surprise that you will get the 0, okay, but try to look into another alternative. In this example, limit x approaching infinity, 5x, okay, over x plus, so I'm using the sum rule property limit, x approaching infinity for sine x over x. So here you can further cancel out. So the first one you'll get 5, and this one you'll get 0. So your final answer will be 5. So I hope that one is clear for this example. It's pretty straightforward. Okay, now for example 1.14 is where we were going to use a special extra step, okay, because we have a fraction or quotient fraction function. Okay, we have, this is fx over gx, and we have limit x approaching infinity, negative infinity. So we may need to divide the numerator and denominator by the highest power of x. Okay, here as you can see, in the denominator, the highest power is x cubed, okay, or x power of 3. So that is why every term in this question, okay, we may need to, each term here, we may need to divide by x power of 3 or x cubed. So when you do that, okay, 4x squared minus 4x squared divided by x cubed, you will get 4 over x, and so on. For the rest, we will have 1 over x squared for this one, and only then you can apply or plug in the infinity value. So we know that 1 over infinity is 0 for this one. Okay, that's why we got 0. So 4 over infinity also 0. This is infinity squared. And then what's left is that we only have 0 over minus 6. So your final answer is 0 as well. Now we go to example 1.15. This is quite a special example because we are dealing with radical function. So last time, if we look at radical to solve the limits using that involve radical functions, we need to rationalize it by multiply by conjugate. However, because we know that this question involving limits, x approaching limit infinity, so since x approaching infinity, so we can use the divide by the highest power. No need to do rationalization method. Okay, now we look into the solution here. Okay, we know that the denominator, the highest power at the denominator is x squared, so that we need to divide all the terms variables here with x squared. So x squared minus 8 divided by x squared as shown here, and as at the numerator, it's quite you need to be careful actually. Okay, I know that you also understand that it must or should be divided by x squared, but if you notice, because we have the square root at the numerator, so you also know that, if I can write down x 3 x power of 4 plus x. Actually we actually divide it by x squared, but we know that x squared can be obtained by x power of 4 square root is equals to x squared. True? Of course true. So therefore that is why we can straight away plug in here x power of 4 square root. So since we are dividing square root over square root, so that is why that's why you can also write down as like this, over x power of 4. So this is what we got for the numerator part. And you simplify it. So once you simplify it, you will get this one at the numerator, and only then you can plug in the value. So if you plug in the value, the solution here is not complete. So if you plug in the value, what you will get is actually, if you apply quotient property rule, limit property rule, so this is 3 plus 1 over x cubed square root divided by limit x approaching infinity for 1 minus 8 over x squared. So again, if you plug in the value, you will get 3 plus 0 for the numerator, and for the denominator 1 minus 0, and your final answer should be 3. Is that clear? Yeah. And for this exercise 1.12, it's pretty simple. Based on figure 1.8, find limit x approach negative infinity and x approach positive infinity, given that this is upper horizontal and lower horizontal. Asymptotes are 1 and minus 1. So this is upper 1, this is minus 1. So if you look closely, limit x approaching negative infinity, so x approaching negative infinity is right here, so it is actually equals to, if I can write it down, x approaching to negative infinity fx, you should get minus 1, and limit x approaching positive infinity, this side you should get equals to 1. I hope you already get a clear picture on this. Very simple. Please try to do exercise 1.13 at home. Okay, I know you are at home, so do it at your comfort home. Okay, and if I may, to proceed infinity limit x approaching c. Okay, x approaching c. So like I said just now in the beginning of this lecture, is equals to when the final answer will be infinity or negative. Okay, let's go back to here. If the values of maybe you can read this part first. Okay, so here, okay, referring to the same figure 1.7. Okay, same figure just now is the one like this. Okay, you see the same figure, we can manipulate the question, okay, asking different question. So figure 1.7 is fx equals to 1 over x. This is x, this is fx. Okay, now this time around we are looking into limit x approaching 0. In previous example we are looking for x approaching infinity. Now x approaching 0 from the right side, and limit for x approaching 0 from the left side. Okay, now look carefully. Okay, 0 from the right side. So 0, where is 0? 0 is over here, so from the right side. Okay, and it's going up to nowhere. We don't know where it stops, so we can say that limit x approaching 0 from the right side for this graph is approaching positive infinity. Now as for the second part, okay, limit x approaching negative infinity, x approaching 0 from the left side. So approaching 0 from the left side is over here, and it goes down here, don't know where it will stop, so the final answer will be negative infinity. Okay, so going up here, so when we're going up here, okay, we will get positive infinity, and when we're going down here we probably get negative infinity. So this is the things that we need to understand. So again, line x equals to 0. So line x equals to 0 is here. Okay, I'm sorry, let me change the color. Okay, x equals to 0 is here. So this is when the we know it as vertical asymptote. Okay, so x equals to 0 is known as vertical asymptote. So by definition, any line x equals to c is the vertical asymptote of the graph function if either limit x approach to c from the right side is plus minus infinity. Okay, and so does x approach to c from the left side. Okay, so here we can say that limit x approach to 0 for this function is not defined or does not exist, because the value from the left side and right side is not equal. Because why? Here we have we obtain not this color, okay, maybe this color, because we obtain from the right side is positive infinity, from the left side is negative infinity, so it's not the equal, the values are the same, so we can say it does not exist. Okay, yeah, maybe we can go and look into example 1.16 to get a better understanding of this vertical asymptote and so on. Okay, so to answer the question, okay, the solution here for fx equals to 1 over x squared. So the solution from the right side is infinity, from the left side is also infinity. So how can we know that? It is actually we obtain it from the graph. Okay, so if I can draw the graph first. Okay, so the graph is something like this. Okay, it's going up, this is going up. Okay, let me draw it properly. It is going up. Okay, right, so as x approach to 0, so this is 0. It is going into infinity from the left side, and from this is, wait, yeah, I don't know what happened to my Apple Pencil. 0 from the right side is 0 from the left side, so both going into infinity. So this is the graph of 1 over x squared, right? And we know that line x equals to 0. Okay, line x equals to 0 is the vertical asymptote. I might have made you confused. So horizontal is something like this. So vertical, sorry guys, I'm not feeling very well actually today. So vertical asymptote is like this. It's like this, yeah. This is vertical asymptote for x. Okay, this is for x equals to 0. I might do some corrections on on this. So the blue one is wrong, yeah. We are not defining it correctly over there. It is actually x equals to this. This is vertical asymptote, yeah. So this is where x equals sorry guys, x equals to 0. And then I might do as well do some corrections on this. Wait, about just now we mentioned about, so our horizontal asymptote, yeah, horizontal asymptote is actually at this point, not the blue one. The blue one is wrong. I'm sorry for making you confused, because I'm also not feeling very well. So yeah, this one is actually y equals to 0. This is the horizontal asymptote. Yeah, sorry for that guys, don't get angry. Okay, we go back to this. So that is vertical asymptote. The horizontal asymptote is for the limits involving infinity. Okay, now now we can say that we go back to this. We can say that for limit x approach to 0 for 1 over x squared, the two-sided limit is equal, which is infinity. Okay, right, now let's look into exercise here. Yep, exercise 1.14. If we can do one question, probably this one. Yeah, so actually this one is pretty simple. 6 over x squared is actually similar to this graph here. Okay, only that it has constant over there. So you might know that the answer should be, what is the answer for this? It should be infinity and also infinity, both from right side and from left side, yeah. And does it exist? Yep, it surely exists. Okay, and draw the corresponding graph, and it should be obtained similar like this. I will not draw it again for you. And I may now proceed with continuity. Yeah. Okay, now for continuity, all right. Maybe you can have a quick read on this. Yeah. Basically, just point out main points here. Continuity for the function curve or line, it has a flow continuously without having any interruptions that due to any breaks or sudden jumps. Okay, so the breaks here, it means like, for example, if we have this quadratic, okay, and then any breaks probably we have here a hole here. Okay, so this consider breaks, so it is not continuous. At this point, maybe this is x equals to 2. And then sudden jumps. Okay, sudden jump, for example, if we have a constant here, and then it jumps going to another line. Okay, so we can say this is a sudden jump. Okay, this is just an example. Okay, now if you look into these points, continuity from point A until point B, so we have all these function curve here is all defined. So if you are interested at this point A, so from continuity from the right, okay, is defined. And if we're interested to look at point B here, continuity from the left, it is also defined. And if we have another point here, C for example, in the middle between A and B, so from the two-sided continuity, it is also defined. So basically, for this graph curve line, the continuity at the points between interval A and B is defined. Okay, between A and B, so it is continuous. Okay, now back to example 1.17, referring again to the same figure 1.7. If you can recall, this is figure 1.7. So does this function continuous, and does it have a point of discontinuity? So basically it is continuous at every point here. Okay, it is continuous, but it has a point of discontinuity at x equals to 0. So at x equals to 0, if you notice, this going straight to positive infinity, this going down straight into negative infinity, and it is not defined as at x equals to 0. Okay. Now we look into continuity at a point. Okay. For continuity at a point, okay, when we want to define whether at x equals to c, okay, c can be any number, whether it is continuous or not, whether it has any break or sudden jump, we need to look or evaluate 3 conditions here. Okay, this is very important for you to remember it. Okay, so condition number 1 is if the limit x approach to c for that function fx exists, then we can say that limit x approach to c from the left side is equals to limit fx as x approach to c from the right side. It means that both of these functions must have or must yield same value. For example, if this yield 1, this is also yield 1. So we can say this function exists. Okay. Condition number 2, you need to see whether that function is defined at x equals to c. So for example, if x equals to c, c can be any number. Okay, it is equals to 1, okay, or any number 2, then we can say that function fc is exist. Okay, this can be any number. Okay, for the answer for it can be any number. Now to satisfy the third condition is when the limit at the first condition here, two-sided limit condition here, okay, the answer for it must be equals to the value at condition number 2. So just now I said if limit from left side and right side is 1, okay, and then fc also got 1, so it means that that function at point x equals to c is continuous since it fulfill all 3 conditions here. Okay, now if if, for example, FC here is 2, okay, we've got 2 here at condition number 2, then we can say that that function at x equals to c is not continuous. Okay, this is not the same kan? So if not the same, then we say it is not continuous. Okay, but if you get answer same 1, 1, so we can say x equals to c is continuous. Not x equals to c, sorry, my bad. We should say that function fx, that function of fx is continuous at x equals to c. This one, fx is not continuous at x equals to c if we yield different answer between condition 1 and condition number 2. So is that clear for now? I hope it is clear to you. Now, if you want to get more understanding, we need to look into example here. Example 1.18. Okay, now in example 1.18, okay, we have here the question asking you to determine whether the following functions here is continuous at x equals to 0. Okay, so to answer this type of question, you need to first identify, to identify. So we already know the problematic point, which is x equals to 0. Now we need to identify which function, because you know, when you want to test the condition 1 and to test condition 2, to test condition 3, especially we start with testing condition number 1, we need to examine the left hand limit and right hand limit. Am I right? So to examine it, you need to check which of this function here. If you look carefully, we have this is piecewise function, and within this piecewise function we have 3 functions altogether. So this is the first function, this is the second function, and this is the third function. Okay, so as for the first function, alright, so look at the x condition here. It says x less than 0. For the second function, it says x when x equals to 0, and the third function, the condition is x greater than 0. So within these conditions, you actually can determine which functions to use when evaluating left hand limit and right hand limit. So as for the left hand limit, we are looking for x less than 0, of course. So this is the function that you need to evaluate. Okay, and then this is for, okay, if I can write down, this is for x approaching 0. Okay, let me change it back using different colors. So this one is x approaching 0 from the left side. This is when x equals to 0, and the third function is when x approaching 0 from the right side. So when you already determine this one, determine first, yeah. So you need to determine first the left and right side limit. Only then you can consider to test the conditions. If you cannot, if you're unable to determine this, then you might probably make a wrong solutions when answering it. Okay, now left hand limit, we know we need to use the first function here, so just straight away plug in, you'll get 2. As for the right hand limit, okay, you use the third function here, so when you straight away plug in the value, you will get 2. And then we can say that limit for x approaching 0 is exist, since limit from the left side, okay, from the left side is equals with limit x approach to 0 from the right side. Okay, now we can happily test condition number 2. So at condition number 2, we are looking f0. What is the answer for that? Or f when x equals to 0. So look at the functions here. You know that you straight away can get the answer, which is referring to function number 2. So the answer is 2. So now we can evaluate condition number 3. Okay, so on condition number 3, so we can say that the two-sided limit from the condition 1 is equals with the value that we obtained from condition number 2. Hence, we can say all 3 conditions are satisfied, and therefore the fx function is continuous at x equals to 0. Okay, this is the conclusion for it. The conclusion, yeah. So you need to write it up. Okay. Is that clear? If that's clear, we may probably go to exercise 1.1. Now let's see some example here. Exercise here 1.15. Okay, we try to do this question 1 Roman. Okay. Okay. Consider gx function. So gx function is here, and we have so many functions. So many functions here. This is piecewise function. So this is function number 1, function number 2, 3, 4, and 5. Okay, 5 functions altogether. So determine if the gx is continuous at x equals to -6 and x equals to -1. So in this question, you actually need to solve 2 conditions, 2 problematic points, which is first x equals to -6 and second one x equals to 1. So because of the time limit, we probably just discuss on how to answer x equals to -6. Okay, so as x equals to -1, you can try to do by your own. I will give you the answer later on. So we solve for x equals to -6. Alright, so for this one, okay, for x equals to -6, again, this we've got some typo here, so maybe you need to do some correction. This is not 6, it is actually -6. This is also -6. Okay, now like I told you previously, you need to identify which functions to use. So for we have altogether 5 functions here, 1 until 5 here. So for x less than -6, this is going to be for x approaching -6 from the left. This is for x equals to -6, and this function, okay, is going to be x approaching -6 from the right. Okay, the right. Now we already identify which functions to use, so let's test the first condition number 1. We look into evaluate limit gx as x approach to -6 from the left. So we have here the second function, which is 1 minus 3 negative 6. Okay, so you should be able to get your answer to be, okay, what is your final answer? Okay, and then if you evaluate limit gx, x approach to -6 from the right, we are going to use x power of 3, function number 3 here. So it will become minus 6 power of cube. Okay, and this one should be negative 216. Right, what is your answer here? Okay, if you solve here, and then obviously, okay, obviously, for condition 1, the value is not the same. Okay, the right hand limit and left side limit and right hand limit are not yield the same answer. Now, for condition number 2, okay, condition number 2, we'll look into what is the value when x equals to minus 6. So our answer is 7, right? This is referring to function number 2, and therefore when we test condition number 3, okay, we know that limit gx as x approach to minus 6 is not equal to it's not f, yeah, this is g minus 6. Therefore we can say all three conditions are not satisfied. Therefore gx is not continuous at x equals to minus 6. Okay, this one is finite. Both values are finite, but the limit x approach to negative 6 from the left side is not equal to limit x approach to negative 6 from the left side. Okay, this is the conclusion for the first condition. I forgot to write it down. Okay, then we test condition number 2 when x equals to minus 6 is equals to 7, and condition number 3, we compare these two conditions 1 and 2. Do they yield the same answer? No. If no, then we can say all three conditions are not satisfied. Okay, and it is not continuous at x equals to minus 6. Okay, that's the conclusion that you need to write down. You can try to do the x equals to minus 1. So for this one, limit x approach to 1 from the right side, you may get 1 if I'm not mistaken. Okay, this one you will get all 1. It will satisfy all three conditions. Okay, so this one also same. Okay, so the conclusion, all three conditions are satisfied. And gx is continuous at x equals to 1. Okay, and then try to do the second question here. Okay, try to do the second question here. And we may need to go to points of discontinuity. Okay, points of discontinuity. Here we have three types of discontinuity. The first one is removable discontinuity, the second one is jump discontinuity, and the third one is non-removable infinity or infinite discontinuity. Okay, so we've got three types that we're going to discuss in a short while. So for the removable discontinuity, okay, it happens when the graph has a hole. at a single x value, and it can occur when factors can be algebraically cancelled from the rational functions. So this function, there is a little bit typo here. So this function will satisfy condition number 1 but violates condition number 2 and 3. So we can refer to example 1.19, 1 Roman and 2 Roman. Okay, this is a little bit typo here, not a major one. Okay, so we go to the second type, which is jump discontinuity. Okay, for jump discontinuity, it is happen when the left hand limit, okay, and the right hand limit exist and finite, but both functions are not equal at x equals to c. So this one, okay, it yield different answer. Left side and right side yield different answer. So we can say fx has a jump discontinuity. So we're going to look into example 1.193. And the final one is non-removable infinity or infinity discontinuity. This is happen when we have vertical asymptote, okay, and on one or both sides, as the function will go towards positive or negative infinity. So this happens when we obtain infinity as the answer. Okay, positive or negative infinity as the answer. Okay, this is going, we are going to refer to example, the last example here. Now let's see, find the discontinuities for the following problems. So 1 and 2 is referring to the removable discontinuity. 3 is jump discontinuity, and the last one is the non-removable infinity or infinity discontinuity. So let's check it out, how to solve this kind of question. Find the find the discontinuities for following problems. Okay, so the question asks you to find. So again, you need to test the condition. So for this one, let me write down the question. So the first question is here. Oh, no need to write down. This is the question. So we just straight away test it. To test the limit question, you need to apply or employ the factorization and cancel method, because we have here the binomial, so we expand to cancel it. So you expand it, you obtain x plus 1 times x minus 1, so that we can cancel this. And then the next step, you can straight away plug in the x equals to 1 and yield 2. Now test condition number 2. When we test condition number 2, we just straight away plug in without using any special method. Just plug in x equals to 1, okay, and you will get 0 over 0 here, okay, when you straight away plug in. So it means that it is undefined. And then you need to test condition number 3. So condition number 3, we are comparing the value from the condition number 1 and condition number 2. So of course it is not the same. One yield 2, the second one yield undefined, so it is not equal. Therefore we can say only condition number 1 is satisfied. So we can say that this function has a removable discontinuity at x equals to 1. Okay, this is how you answer it. Now to test condition number 2. So condition number 2, okay, I may need to write down the function here, because it is okay, fx, we have piecewise function 3x minus 5. This one we have 2. This is x not equal to 1, and this is x equals to 1. So when it is not equals to 1, it means that we can use this first function to evaluate the two-sided limit, or to test the first condition. So we use the first function here. Since it is a simple function, we can just straight away plug in the value and the result yield -2. Okay. Now we look into second condition. Okay, we already test the first one. Now the second one. So at x equals to 1, it means that we're referring to the second function. So the result yield 2. So we have -2 and -1. -2 and 2. Okay, -2 for the first condition and 2 for the second condition. Okay. So it means that when we test the third condition, it does not equal. Therefore, since it only satisfy condition number 1 and condition number 2, but not number 3, so we can say that this function has a removable discontinuity at x equals to 1. Now we go to the third example, which discuss about jump discontinuity. So this is the question. It's a piecewise function to x. This is for x less or equals to -2. The second function, x cubed minus 6x for x greater than -2. Now there's a typo here. Okay, it's okay. We solve one by one first. We test the first condition from the left hand limit. So for the left hand limit, it means that we need to evaluate the first function here. This is the second function, yeah. So our first function is here. So the typo is here. It is actually x squared plus 2x. Okay. So when you plug in the value of 2, you will get 0. Okay. And then when we test the right hand limit, so the right hand limit, we pick the second function here. So when you plug in 2 into the second function, it yield 4. So again, the left and right hand limits are not equal. So it does not exist since condition 1 is violated. Okay, so we can say that this function has jump discontinuity at x equals to -2. And then we go to the final example. This is for non-removable. The question here is stated here, so I no need to write it down for you. In this example, this is fraction, polynomial, or rational function. So you need to factorize it at numerator and denominator. So we can see that we have the same common factor, which is x minus 2. So we can cancel it out. What's left is here, and then we just straight away plug in x approach 4. And when you straight plug in this one, it yields 7/0. So when you get this type of answer, so it means that we know that x equals to 4, okay, is the vertical asymptote for that function. And so we can say that this function has a non-removable infinity at x equals to 4. Alright, so this is quite a long explanation. I hope you can bear with that. Yeah. You probably can try to answer this exercise 1.16. Maybe try to answer this question. Okay. This one quite need a long explanation. Okay. So let's try to do this one first. Okay. Consider fx function. Okay. We have piecewise function. Now find the limit as x approach to 1 from the left side and x approach to 1 from the right side. So according to this function, I believe that you already know how to answer it. So if from the left side, you are looking into first function here. So if you pick this one, you are correct, and direct plug in, you will get 3. Okay, and from the right side, if you direct plug in this one on the second function, you will also get 3. Okay, now what does this tell you about? Okay, you can say that this limit is exist. Okay, it is exist and at x equals to 1. Okay, that exists at x equals to 1. Okay, exists since, okay, since both equal to 3 at x equals to 1. So is fx continuous at x equals to 1? This is quite a tricky question. If you answer yes, then it is wrong. So fx is not continuous. Why it is not continuous? You look carefully at the conditions here. There's no condition says x equals or x less or equal to 1, or this says x greater or equals to 1. There's no equal symbol. So if there's no equal symbol, so we can say it is not continuous because, okay, it is not continuous at x equals to 1 because, okay, f1 is not defined. So f1 is not defined on this specific function here. Okay, so I hope that one is clear. Try to do this question at home. Okay, exercise 1.161 Roman. And also you can proceed with tutorial and discuss your answer with Dr. Nazib, okay, during tutorial session. And I think with that I end my lecture session for this section 2 class, and we're going to continue our lecture on chapter 2, which is differentiation and differentiation. Okay, so we're going to look into differentiation topic chapter 2 on next week lecture. Okay, until then, all the best.